this week we have an excellent speaker that I am very excited to welcome. So we have Ana Asenjo-Garcia from Columbia University. So Ana is one of, I would say, the rising stars of theoretical quantum optics. She's wonderful and knows many things. So she got her PhD in Madrid and then did postdocs at ICFO with Derek Chang and at Caltech with Jeff Kimball before starting her own group at Columbia in January 2019. And so she studies all sorts of things of collective emission of atoms in various geometries, waveguide QED, and she's going to tell us all about it. And so with that, I give you Ana.
Thank you. Okay, thank you so much, Alicia and Liz, for the invitation. I'm glad to be here today. So I'm going to be talking about Dicke superradiance and basically many-body optical decay from atomic arrays. So I should start by saying that if you have any questions, also for those of you that are in Zoom, I'm happy if you stop me at any time so then I don't bore of hear myself. Okay, so today I'm going to be talking about physics that is emergent and happens in complex phenomena, such as, for instance, so what is an emergent phenomenon? It's something that happens in a complex system, and if we try to understand it from first principles, or try to understand what happens at the level of a single particle, we would never be able to guess what happens when all these particles get together and interact. So an example of that is a snowflake. If we understand it to death, we would never guess that when many of them are together, there will be an avalanche. And the biological realm, an example is a firefly. So fireflies, when they get together, they synchronize and radiate light in bursts. And at the level of quantum optics, I'm going to be talking about a phenomenon called Dicke superradiance that happens because atoms see each other through vacuum fluctuations, and this leads to an enhanced photon emission. And I will make a case that actually is some hybrid of a photon avalanche that happens because of atomic synchronization. So the idea behind many of the, much of the physics that my group does is very well characterized by this phrase that you can find in the lecture notes of Ray Glauber for the Summer School of Les Hous in 1964, which are wonderful if you haven't read them. But as I was reading through them to prepare my quantum optics class, and I found this phrase that I thought was fantastic. And so he says that all of the delicate and ingenious techniques of optics are exercises in the constructive use of noise. So I really resonate with this, and via the fluctuation dissipation theorem, you could also say that all the techniques in optics are about the constructive use of dissipation. And what I want to harness today is collective dissipation. And so this is what I'm going to be talking about. So what we work on is in systems where you have multiple quantum emitters. So today I will be talking mostly about atoms. I will talk about superconducting qubits by the end of the talk. But when I say atoms, you have to think of, quite globally. This could be a neutral atom, could be a defect in a solid, or it could be a superconducting qubit. It's something that talks to light in a dipolar manner. And so when many of these, I think I touched the wrong button. Let me go back. Now forward. Okay, I have to record. Okay. Fast forward. Yeah. Okay. Okay. Well, so when many of these atoms share an environment, they are gonna be talking to each other through this environment, and so dissipation is not a problem that needs to be curbed, but instead can be a resource, because through dissipative interactions, there might be atoms become correlated and also entangled. So one can enhance the coherence of a system because one can, the lifetime of a quantum state is no longer determined by that of a single atom. It can either be accelerated or it can be, the lifetime can be enhanced or it can be suppressed. And the idea, I'm going to be talking about atomic arrays. And the idea behind this is that, as I will show later, a collection of atoms will give rise to robust behavior. So instead of trying to engineer to death a quantum system that is isolated, I want nature to do part of the engineering for me. So I want robust behavior that arises because of collective interactions. So I think that quantum optics in atomic arrays merges two distinct fields in physics, that is that of quantum optics and condensed matter physics. So when people started thinking about quantum mechanics, this was because they were interested in the nature of light. So they were seeing the emission. Oh my God, this is gonna be cut. I mean, at least you know what is gonna happen. It's like a preview. Okay, I'll try to not do this, but I'm sure that this is gonna happen like 10 more times. But anyway, so when people were looking at the emission spectrum from atoms, they would see like these discrete lines. And so Bohr came up with the model of the atom that we know that is not correct, in the sense that we know that electrons are not circling around the nucleus, but he got something right. That is the fact that energy is discretized, and so the electron jumps from one orbital to another and emits a photon. And so if you care about the behavior of electrons, you may become a condensed matter physicist and start trying to understand what happens when many atoms are together forming a material and the electron hops from atom to atom. And so then you realize also that this is perhaps not the behavior of a single electron, but there is collective phenomena, and this gives rise to correlated states of matter. If you're instead interested in what happens to the photon that leaks from the atom, then you become a quantum optician. And so in quantum optics, at least as I said, it has been mostly about two distinct areas. One is about basically preparing exotic states of light. So for instance, coherent states like lasers, or even more exotic like purely quantum states of light like Fock states. And then in parallel, people have tried to understand the most toy model-like picture of light-matter interaction, that is a single atom interacting with a single optical mode in a cavity. So this is cavity QED. And the idea behind atomic arrays nowadays is that I think they really connect these two pictures, because you have a lot of atoms together. They are going to be interacting with the optical field. But then, because of the inherent complexity of the system, new physics, collective physics, is going to arise. Okay, so just to nail down what is the difference between a condensed matter system and an optical system, I want to present you, what I think are the two main differences. So both of them arise from the fact that an electron has charge and a photon does not. So this has very strong consequences. First, photon number is not conserved. So imagine that we have a wire and we apply a potential. The electrons are gonna flow throughout the wire from one side to the other. If I try to make the same, analogy in an optical system, I would have an optical fiber. I will shine a laser at a given frequency, and the photon is going to propagate through the fiber because the fiber has a refractive index. So now, if I place a defect in my waveguide, then the photon has three possibilities, or it doesn't matter, a classical light has three possibilities. It can be transmitted, it can be reflected, but it can also jump outside the fiber. So that's something that does not happen in traditional condensed matter systems. This is because optical systems are inherently open. The second thing that is different is that in contrast to electrons, that they see each other via the Coulomb interaction, photons do not interact with each other. So if a photon comes and crosses another, they would not see each other. And this means that to make photons interact, they need to be interfaced with matter. And so for me, matter means atoms or other type of quantum emitters. So today I'm going to be talking about many-body physics in optical systems, which means that atoms are going to be interacting with each other dissipatively. So I just wanted to mention that the...
Excuse me, Anna.
Yes.
Maybe I could ask a question. This is Bill Phillips.
Yeah.
So in your list of things that photons are different from electrons, you left out, or at least I didn't hear you say, that photons are bosons.
That's also true.
Is this a big deal?
I think it can be. It won't be for the type of physics that I'm going to be talking about today, because the atoms are well separated. But if you consider things like quantum optics in condensed systems, then the statistics will show up in how these systems scatter light. I don't know if that answers your question. Yeah. Okay. Sure. But that's a good point. So I didn't mention that. Okay. So as I mentioned, I'm going to be talking about atomic arrays, and I'm going to be mostly talking about many-body physics in these systems, but I just wanted to mention that atomic arrays have been proposed as very efficient light-matter interfaces because when you have many atoms together in an ordered array, there is interference processes that make photon absorption and emission very efficient. So we have suggested using ordered arrays close to a fiber to improve the efficiency of quantum memory exponentially. We have used the fact that atomic arrays support what are called dark states that do not scatter photons out to use them as a waveguide where you can couple impurities to this array. And then these are works from other groups where they have also realized that 2D arrays can behave as perfect mirrors, perfectly reflecting light. And if you arrange them right and they have the right atomic structure, they also support chiral modes because they are topological. So this idea of using atomic arrays as mirrors has been recently realized. So this is an experiment by Immanuel Bloch, where they send light, the atoms are separated by less than a wavelength. And you can see here, the reflectance reaches 60%. So in theory, this can be as high as 100%. This is another example of a recent experimental development in the group of Antoine Brouwys, where they have a 1D array of atoms. The resolution here is not good enough, but it's a 1D array of atoms. And they send light, and through the collective shifts, they see that atoms are interacting with each other. So these experiments and the previous works are all in the single excitation regime, where only one excitation or one photon is shared among all of the atoms. And the question that I want to answer today is what happens for many excitations. And this is generically a hard problem to solve. Yeah.
What knob turns you from single excitation to video excitation?
So
intensity,
yeah, it depends. So intensity of your laser. So if you're pumping, right? So as you increase the intensity, you will saturate the atoms. Another option is you could maybe not do continuous pumping, but you could do a pi pulse. And so that will put the atoms in the excited state. But yeah, basically intensity. So if you don't shine light on your atoms, they would be on the ground state. The more shine you light, the more light you shine, the more highly excited they become. Yeah. Okay, so then the question is, what happens? So at the level of single excitation, calculations are basically almost trivial because these are just like antennas. Okay, but then as you start increasing the excitations, things become very non-classical, but also more complicated. And so the first example of many-body problem in quantum optics that I know of is Dicke superradiance. So Dicke in 1954 wrote this paper. And so I want to read at least a few sentences of the abstract. So in the usual treatment, he says molecules radiate independently from each other. This simplified picture overlooks that molecules are interacting with a common radiation field. The model is wrong in principle. Okay, so what he's telling us is the following. If we have atoms or molecules that are really far away from each other, they do not see each other. Therefore, if we excite them, they would radiate independently from each other. So their photon emission rate here versus time will be this exponential. On the other hand, when molecules or atoms are very close to each other, then as they decay, they start synchronizing. They start talking to each other. And what this means is that if we look at the photon emission rate, it's going to grow up to a point where there is a huge release of energy that is called the superradiant burst, and then it decays. So this is an example of macroscopic. Oh, yes, sorry.
This basic function, when they are really together on top of each other, and then they are basically interacting the same mode of the.
That's right. Yes.
Could you repeat the question, please?
Oh, yeah. The question hasn't finished yet, so maybe you can ask it and then I will repeat it.
So
Yeah.
why do we expect that they are not really in phase at the beginning, and then only takes time, like only just a certain amount of time later they take?
Yeah, that's a very good question. So the question is, why shouldn't we expect them to be coherent from the beginning? And instead, it looks like it takes a bit of time for them to become coherent. And so in the case of Dicke superradiance, you prepare the atoms all in the excited state. So this is a product state. And so initially the state has no coherence whatsoever. There is no dipole moment at all. And then it is only when atoms start decaying, that this dipole moment starts to grow. And so what happens is as they decay, even though that is a purely dissipative process, there are, they start interacting and building coherence. Okay, and that coherence leads to a macroscopic dipole moment that becomes huge at the point where half of the atoms are excited. And then they go to the ground state. And so what you see is like initially very little coherence because they are all in the excited state. Then through this decay, they develop this microscopic dipole moment, and then they continue decaying up to a product state that is all the atoms are in the ground state. So like it takes some time because it's the time that, where interactions are building up. And it doesn't continue growing and growing because you have a finite energy in your system. So if you want to think about it from the perspective also from the Hilbert space, you go from all the atoms excited to all the atoms in the ground. And through the decay, what you're doing is you're exploring a huge Hilbert space that becomes very large just at half excitation. And then it goes down in size again. Does that make sense? Okay, so I think I don't have to then explain anymore because that helped me. And so basically it's a process of synchronization, right? And this happens purely through decay. And so to give you perhaps a bit of context, I want to take a detour and talk about fireflies, mostly because I promised it also in the introduction. So fireflies using bioluminescence to attract mates or prey. And some species of fireflies synchronize. So if there are many fireflies, they see their neighbors via their eyes, and they accelerate their internal clock such that after some time, a spontaneous order emerges. So here is a video that was taken in, I think, Indonesia. And so you see them synchronizing. And so this is an example where each of them will fire with its own clock, but at random, if they are very far away from each other. If they are close, they synchronize and then they become ordered. Okay, so same as atoms, same as fireflies, many atoms radiate differently, not just more, and this is critical. So this is precisely what superradiance is, and superradiance has been observed in multiple systems. So this is an example of superradiance in a Bose-Einstein condensate, superradiance arising from perovskites, so this is a solid state quantum system, and also in cavities, of course. And it's not only a cool many-body phenomenon, but it also can be used for applications. So people have used superradiance for developing superradiant lasers. So these lasers, in contrast to regular lasers, operate in the bad cavity regime. And the mirrors, the cavity is not very good. And the mirrors this laser is basically more resilient to thermal fluctuations in the mirrors because the coherence is stored in the atomic medium. So basically, Dicke solved the problem already. So why am I here, you may ask? And the answer is that he solved it in a situation of high symmetry. So basically, all atoms talk to each other at exactly the same rate, which means they are either all in the same spatial location or in a cavity. And the big question is, what happens in extended systems? And this has been a debate for many years. So this is a review on Dicke superradiance from 1982 from Gross and Harosh. There is a section on it about what happens in extended geometries. And the issue, at least that's what I think they thought based on their paper, is that if you start spreading your system, there is dipole-dipole interaction. So there is the dissipative part of dipole-dipole interaction, but also the coherent part. So there is a near field interaction that appears in the Hamiltonian. And they thought that the fact that the atoms are separated now from each other is going to produce local defacing that is going to quench superradiance. And so they came up with ideas to how to overcome this. And one idea is, okay, let's put the atoms in a ring. And so there is now particle exchange symmetry, and this may preserve superradiance. On the other hand, this is all hypothetical because in 1982, no way that you can do this numerically, like it's impossible. So nobody could do that back in 40 years ago. Okay, so in 1992, perhaps this was hypothetical, but now it's not hypothetical anymore, at least from the perspective of experiments. So in the last 5 years, there has been a huge advancement in experimental physics with respect to building ordered atomic arrays. So this is an example of atomic arrays built with optical twisters. So every point that you see here is an atom fluorescing, and so trapped with a tiny twister that then can be rearranged to form an ordered chain. Here you see how to generate 2D order arrays from a square to heart. And then you can become more creative and start producing landmarks of your city. So this is Chicago, and this is an Eiffel Tower. This is from the group of Antoine Brouet, and they are in Paris, so they can even create a 3D Eiffel Tower. There are other ways to create arrays. So this is, for instance, an example, recent example of solid state emitters that is realized by placing a 2D material on top of silicon nanopillars that produce a confinement and a quantum dot that then fluoresces. And arrays can also be generated in other type of systems like waveguide QED, where you have superconducting qubits coupled via a 1D transmission line. So this is, there won't be talking through a 3D bulk vacuum, they will be talking through a 1D vacuum, okay? Okay, so then if we try to guess what is going to happen is the following. If the atoms are really far away from each other, the field decays in free space, so they should not see each other. So we should see in the limit of distance going to infinity, a photon emission rate that is monotonic with time. Okay, good. If we place them all at the same point, they talk to each other at the same rate. So we should go back to the picture of Dicke, where the peak of maximum emission happens at a time that is different from 0. And the question is, what happens in between? And the answer is that knowing this is exponentially hard. Like, it's in principle impossible to know for a large number of atoms because the Hilbert space scales as 2 to the n. And that's a problem to do any type of computation. Okay, so then I'm going to try to approach the problem. And so I'm going to build the intuition. So we're going to first look at what happens at the level of a single atom, how it decays from the excited state. Then I will talk about a collection of atoms. So when we have, let's imagine that we have an atom. This is a 2-level atom for me. I'm a theory, so this is the easiest I can do. I'm going to place it at the excited state, and I'm going to monitor it. And so if I look at the population in the excited state, is 1 up to a point where a photon is emitted. The atom goes to the ground state. And this process of photon emission is called basically a jump. And it happens because this jump operator, that is a sigma minus type of operator, acts on the excited state and brings the atom to the ground state. Okay, so this process is stochastic and it is driven by vacuum fluctuations. So this means we cannot control exactly when this is going to happen. So if I repeat my experiment again, I put my atom again in the excited state, and I monitor it again, it will jump at another time. And then if I do it again, it will jump at another different time. So this means that when I take the average of all these trajectories, what I would recover is the density matrix type of evolution, the ensemble evolution, where the decay from the excited state happens at an exponential rate, and that rate is determined by, is the spontaneous emission rate that is determined by the environment. And so again, we have a situation where we have a lot of stochasticity because it's an open quantum system, and photons are basically detected at random times, but are also detected at random directions. And when I average overall directions, I should recover a dipole emission pattern. Okay, so this is the picture of a single atom doing a quantum jump. So then let's try to understand what happens when we have many atoms. So when we have many atoms, the problem is hard. Why? Because we have n 2-level systems, so the Hilbert space goes as 2 to the n. And then in principle, they might be in vacuum, so we have infinite optical modes. So we have a horrible Hilbert space. So what we do is we integrate out the electromagnetic modes, and we end up with an open quantum system that has long-range interactions that are coherent and dissipative. So then when I integrate out these degrees of freedom, I end up with an atomic density matrix that is evolving following this equation. And this has 2 parts. One that is the coherent evolution. This conserves the number of excitations and is driven by the Hamiltonian. And I have another part that is the Lindblad, which is the part that accounts for dissipation. And that rate, gamma ij, tells me about how atom I and atom J exchange photons. And the rate of that is determined by the imaginary part of the propagator of the electromagnetic field in free space. I'm going to be talking about free space. And so in free space, that propagator is that. So it scales as 1 over r cubed, 1 over r, 1 over r squared. Okay, and so this is textbook. Is just if I have a dipole here, it produces a field here, and so the propagator is just the Green's function. Yes.
Can you just talk about a little more detail about what was the composition of the coherent?
Yeah, sure.
Number of layers?
Yeah. So the question
Can
is
you
if
repeat
I
the
can.
question?
Yeah, I'm gonna repeat the question. So the question is if I can talk about what is a Hamiltonian. So the Hamiltonian is basically a spin flip Hamiltonian. It's a sigma plus sigma minus. It also emerges because of dipole-dipole interaction, and actually the rate of exchange of excitations is taken instead of by the imaginary part of the Green's function by the real part of the Green's function. Does that make sense?
Yeah, so anything that does not radiate to the environment is.
Yeah, so basically it's like when you do this tracing out, you have a part that is resonant with the frequency of the atoms, and this means that you can emit a photon that is on shell and can propagate, and then you have a part that is off resonant, and so you're integrating over all frequencies, and that gives rise to this real part of the Green's function. So it's basically dipole-dipole interactions, but that they are not dissipative in nature. So they involve some phase exchange, if you want, not loss of actual energy. So basically, if you look at, again, from the picture of Hilbert space, if you go down from the excited to, if you have many atoms, so they are all in the excited, and here they are all in the ground, and in between you have like different subspace of different number of excitations. The Lindblad goes down, makes you go down and emit photons, and the Hamiltonian will rotate you in this horizontal plane of fixed number of excitations. So it would be more like what you would have in a closed system, regular condensed matter system. You wouldn't have these parts that bring you down in excitation. Yes?
When you write a Lindblad equation like that, you're telling me that in the process, this atom emitting a photon and atom absorbing the same photon, they've entangled with some degree of freedom. Yeah. What is that degree of freedom?
Yeah, I can. The question is, in the picture where I emit a photon, an atom I emits a photon that gets picked up by atom J, they get entangled through some degree of freedom, optical degree of freedom. What is that degree of freedom? Okay, so this is all in the theory of open quantum systems. So what you do is you have in principle a Hamiltonian that has, like, if you're in a cavity, this is free space. So let's just go to free space. I can answer the same question in a cavity, it's basically the same, but you have a collection of optical modes that are bosons, so they have their own entities, and you have the atoms that are spins. And so indeed you have a type of dipole Hamiltonian, so B times E, so you have sigma plus A plus sigma minus A dagger, etc. What you do is you integrate this A, so basically you're saying that you're under the Born Markov approximation, which means that the entanglement that you generate with the bath is actually not that large. You're mostly entangling atoms via the bath, but the correlations, the memory in the bath just like goes away very fast. Okay, so there is like you don't need to keep the photons as true degrees of freedom. They just behave as this propagator of the interaction.
So there's some other process in the cavity nodes that's much faster than this process and results in.
Yes. So there is exactly, yes. So you can think about it from the perspective of timescales or from the perspective of bandwidth. What this means from a frequency perspective is that most of the frequency response is dominated by the atomic line width, and the bath is just something that is very constant in frequency. It doesn't have any sharp feature. So if you want to think of cavities, for instance, this works very well in a bath cavity, but in a high Q cavity with very narrow line width, where the photons are really there for a very long time, you cannot do this. In free space, which is what I'm talking about, you can perfectly do that. Yeah. Okay, any other questions? Yes.
If I'm reading this right, this equation actually isn't in Lindblad form because sigma j plus is not sigma I minus dagger.
Sigma j plus is not
Sigma I minus dagger.
sigma
I
j.
bet the sum on INJ.
And so I was wondering, yeah, if interchanging took care of that, or if there were like.
No, I think it
minus
is.
terms that got
Yeah, it is in
neglected.
the blood form.
It is. in the-
Yes,
Okay.
and we can discuss it later if you want. Yeah. Okay. So fine. The important thing here is, okay, let me just recap. We have the Hamiltonian, we have the Lindblad part. I'm very concerned about process of superradiance where you emit photons. So it makes sense that the part that I'm going to be most interested on is this second part, okay, the dissipator here. So what I'm going to do is I'm going to take this part of the equation and this matrix, that is the matrix formed by the interaction between atom 1 with itself, atom 1 with atom 2, atom 1 with atom 3, I'm going to diagonalize it into a set of collective modes. And so this is what I have here. So then these are now collective jump operators. So for a single atom, I had a sigma minus that drew me from the XIT to the ground. Now I have a collection of atoms. I don't know which one goes to the ground. So then now I have a superposition, sum over j's, with some spatial profile that just comes from the eigenvectors of this matrix. And the eigenvalues are the decay rates. And this tells me how bright is this decay channel. So if the decay rate is very large, it means that this jump operator, this process of decay, is going to act frequently. And if this decay rate is very small, it means that it's very unlikely that it acts on the atoms. And so these are collective jump operators. There are n of them, and each of them corresponds to emitting a photon. This process of emitting a photon is going to imprint phases on the atoms. And it also is going to correspond to a very well-defined far field emission. So there will be some process of decay that will result in photons being emitted in your direction. There will be some other process of decay, some other jump operator that will involve photons being emitted in that direction. Okay, so that's what these collective modes represent. Yes.
So I'm a little hard to understand what does it mean by eigen mode of the decay when the dissipation process. So when you say like I think you're equating like the eigen mode of decay and the collective decay mode, they're the same thing.
Yeah, they are the same. So collective mode of decay or jump operator is just an eigenstate of this dissipator matrix. So it just tells you that in the previous basis, I had like an individual atom basis, but now I'm gonna look at what happens on all of them collectively. So then I have to diagonalize this matrix, and this matrix, the eigenvectors are gonna have support on all the atoms. And it means just that when my array emits a photon, that process of decay is going to prepare each atom in some phase. So imagine that you're in a cavity, all the atoms are excited, and there is a process of photon emission. I'm going to explain that with the cavity in a second. That is going to prepare the atoms in a superposition of all the atoms excited except one in the ground state. And it can be the first, the second, the third, and so on. So it's like a perfectly permutationally symmetric state that you prepare. Yes.
So can I say that when you like there in principle, there's no way to distinguish like where exactly this single photon
Yes.
is emitted, and then you can say there's
Yes, it's exactly that. Yeah, yeah. But this is seen from the perspective of like the phase that is imprinted of the atoms. But then at the same time, if you look at, you can relate that spin excitation that you're preparing with some far field profile for the photon that you're emitting. But it is precisely what you're saying. Yeah. Sorry, I think I forgot to answer, like to repeat the question, but anyway.
Well, this is Bill again. I did hear the question as it turned out, but now it seems like what you've described is, in a sense, the inverse of the more usual thing that we think of when we take an ensemble of atoms and we excite it with a single excitation that is shared among all the atoms. You've
That's
got
right.
all the atoms starting to excite, and then, in a sense, the de-excitation is shared among all the atoms.
Yeah, it's yes. So like a jump operator would produce this decay, and the dagger version of it will produce an absorption of the photon that has that spatial profile to go up. Which
Right.
is the
Now, what I'm
process
wondering
that
is,
Yeah.
is it is it pretty much the same thing, or is it something that is, I don't know, n factorial times more complicated?
No. It's exactly the same thing, and that's the beauty of it. So the physics that I'm going to talk about is like 2 to the n Hilbert space, absolute mess. But at the level of the description of the master equation, I can do that with a complexity of, it's an n by n matrix. It's just that I'm going to have many of these successive events acting, and that's what makes it complicated. Does that make sense?
Yeah. Okay. Thanks.
Yeah. Okay. So it's good that we're discussing this so much because it's kind of critical. So let me move on. So what I want to calculate is superradiance. So I want to look at the photon emission rate. So the rate at which the system is emitting photons is minus the rate at which the system gets de-excited. And so the rate of de-excitation is the derivative of the total excited state population, which I can relate with these collective decay rates and these jump operators. Okay, so that's only to know what I'm calculating. Okay, so I'm just gonna look at Dicke superradiance in a cavity because it's the easy example, and then we're gonna make it more complicated. So if I have many atoms in a cavity, they all talk to each other at the same rate. This means that there is only one relevant jump operator, which is the permutational symmetric jump operator. All the others have rate of action 0. And this means that the problem is exactly solvable. And so the process is, as I described before, all the atoms are initially in an uncorrelated state. Process of successive photon emission produce these permutationally symmetric states, so where you don't know which atom got de-excited, and so you go down. And as this happens, you're building this macroscopic dipole moment. So this resembles basically a photon avalanche, where the skier is a quantum fluctuation that gives rise to this decay in the form of photons. And this happens all because we are in a very well-defined grid, which is the cavity, and controls the boundary conditions and just tells me there is only one way for the snow to go down. Okay, that is to the cavity mode. Okay, so then let's see what happens in free space. So in free space, in principle, the interaction depends on the interatomic distance, and there is a lack of symmetry that makes the problem very complicated, because now atom 1 talks to atom 2 at a rate that is different from atom 3, and so on. So I cannot do this simplification. So generically, if my interatomic separation is 0, I have only n permutationally symmetric states. This leads to a burst. If my interatomic separation is infinity, I have n single particle states that I care about, and the decay is exponential. And if the interatomic separation is finite, I have 2 to the n states. I don't know what happens. Okay. So then let's see, the first thing that one can do, thanks to computers nowadays, is to just put it in a computer and see what happens. So this is the normalized photon emission rate versus time. And this is for a distance of 0.1 lambda 0. So the atoms are reasonably close, but still the whole array can extend beyond a wavelength. And we see multiple things. The first thing is that the dimensionality matters. So 1D chains and rings behave in a way that is perhaps for superradiance worse than 2D arrays, even though, rings seem to behave better, but it turns out that they don't. The second thing is, so dimensionality matters. And the second thing that is important to realize is that I can do this calculation. Actually, my postdoc can only do this calculation for 16 emitters, and this takes a few days, or I think 2 days in Columbia's cluster. So this is highly depressing, because even though this looks very cute, in reality, this is a 4x4 array, and I cannot do 5x5. So if this is all I can do, I cannot tell you anything about Dicke superradiance in extended systems. Yes, Christopher.
The 4x4 array seems more like a 0D system than a 2D system, right? Because that's like less than half a wavelength.
It's more mean field. Yes.
Oh, okay.
Yeah, I'm gonna talk about that in a second. Yeah, sorry. The question was, a 2D array looks more like a cavity system than a 1D array. Yeah. Okay.
So the number 16 seems like a practical, boundary that you can practically calculate.
Yeah.
And then you want to make it kind of make it universal. If you try less number of atoms, and then is it like basically the same thing, or there's some kind of?
Yeah. So the question is, how does this scale with n, right, with atom number? And the question is, it's very hard to answer from here, because, for instance, for 2D arrays, you can do 2x2, 3x3, 4 by 4, I cannot do 5 by 5. I don't think anybody in the world can exactly simulate the dynamics of a 5 by 5. And in 3D, I cannot even do 3 by 3 by 3. It's just highly depressing when you think about it. But I'm gonna.
This afternoon, I think we should just let her.
Okay, yeah, I'm gonna be talking about the scaling with n because that's important. Anyway, okay, yeah, so I should move on. So is this all we can do? If it were, I wouldn't be giving this talk. So yes, no, we can do more things. And so let's see what we can do. The first thing is we can switch on and switch off the Hamiltonian. I can do the same simulation without the Hamiltonian. And what you see is that there is no difference. There is not very big difference. So again, this process of superradiance is driven by the dissipative part. The Hamiltonian does not seem to do much. That's good. Some simplification. The second thing is that this is for an example in 1D, but it applies in any dimension. If we start looking at a system where all the atoms are together, as we spread our chain, what we see is that this goes from a burst to this exponential decay. And what you can see is that you could guess that just by looking at t equals 0. So this is a process of synchronization, which happens, either it happens in the beginning or it does not happen. So if we just look at t equals 0, we should be able to guess whether a burst is going to happen or not. And so that is how we're going to overcome the exponential complexity. Luis, did you have a question? No, okay. Okay, so atoms synchronize at the beginning or not at all. So then what it means is that we can define a minimum burst, which means the second photon is going to enhance the first. This is the bare minimum for superradiance. It doesn't mean that the burst is going to be enormous. I cannot tell you, but I can tell you that this is the minimum requirement. And so what I can do is I can define this in terms of a second order correlation function, that is the ratio between the probability of emitting 2 photons divided by the probability of emitting 1 photon squared. If this is larger than 1, then the second photon will be emitted faster than the first. And what we can do is we can calculate that. So this is the number that we have to calculate. So we can do that in a page, basically. And the result is surprising. Not so surprising once you understand it. This is the result. So D2 larger than 1. So minimum conditions for superradiance is equivalent to the variance of the set of decay rates, properly normalized, has to be larger than 1. So what does it mean? What it means is that we want all the photons to be emitted in a dominant decay channel. So in the case of the cavity, we only had one because of boundary conditions. Therefore, superradiance is guaranteed. In free space, in principle, we have n of these because the photons can be emitted in many directions and this imprints different phases. And so what we want is to suppress some of these and enhance some others. And so besides getting insight into what drives superradiance, this equation is also useful because we have gone from evolving 2 to the n differential equations to diagonalizing an n by n matrix. So we have reduced the complexity a lot. And now we are going to be able to answer questions like the one you asked me about the scaling with atom number. Okay, so this is just to say that this is true. What it means is that if we have a small set of relevant jump operators, we should have superradiance. So again, this is a 1D array. This is the superradiant burst. And this is a very complicated plot that I'm going to try to explain. Initially, all the atoms are in the excited state. They go down to the ground state. I have 8 jump operators, 01 to 08, that I have ordered from most radiant to least radiant. This is effectively in a cavity or distance equal to 0. There is only one relevant jump operator that is going to act, the permutational symmetric one. So these others are completely dark, and I only have one that is bright. And what you're seeing here, these lines represent of 1,000 trajectories that we're doing in this. We're exciting 8 atoms, seeing them decay, and doing this 1,000 times. We're looking at the statistics. So 1,000 times, only the jump operator acts all the time. So just to give you some context, if now I separate my atoms by 0.1 lambda, what I see is that some of these jump operators become bright. And this is because now in free space, we have interference. So if this means that there will be operators that are bright because emission in certain directions is enhanced. And there will be operators that are dark because of destructive interference. So as we increase the distance, some of these operators become bright and they start competing, and this leads to a decreased burst. And if I separate them even more, you see that many of these jump operators act, and this leads to this exponential suppression in the photon ray. Okay, so this seems to confirm our intuition, that is the competition between jump operators is what kills superradiance. So dissipation gives you superradiance, dissipation takes away superradiance. So it can go both ways. And so just to mention, the interatomic spacing is actually the parameter that controls the number of important decay channels. So I'm going to explain this in 1D, but this holds for 2D and 3D. So imagine that we have an ordered array of atoms separated by a distance d. I can plot the decay rates versus wave vectors. So now I'm going to go to the infinite chain limit. So I can order these decay rates in terms of wave vector, and in between the light lines that are determined by the wave vector that is ω0/c, basically the maximum wave vector that any photon in free space can have, I have decay rates that are larger than 0. These are bright operators. And outside, I have dark states. So I have destructive interference and dark operators. So if now you have a finite chain, this is going to sample this dispersion relation, which means some of my operators will be bright, some of them will be dark. And so in 1D, dark decay channels only exist below λ/2. In 2D and 3D, that critical distance changes. But basically, the important thing is that the relative number of dark and bright operators changes with the interatomic separation between the atoms. Okay, so this is just a plot that shows that indeed the second order correlation function, or the variance, is a good figure of merit for superradiance. So I'm plotting here the time of peak emission versus the second order correlation function. I said that beyond, if this is higher than 1, then I have superradiance. If it's not, then I don't. And so if I don't have superradiance, the time of maximum emission is 0, and this is what I'm seeing here. And as soon as I cross this, then I have a peak emission that is finite. So this means that this is actual numerical calculations, and this figure of merit that we use is good. And so now that we have a good figure of merit, now we can answer the questions of the scaling. So this is a plot of the critical distance, that is basically the separation beyond which superradiance is lost, versus atom number. So in 1D, we see that the critical distance for different polarizations that a dipole can have in a chain, so either perpendicular or parallel, it saturates to 0.3 the transition wavelength. This is confirmed by calculations that one can do in an infinite chain. And so the numerics and the analytical calculations agree. And so if superradiance occurs only below a critical distance that does not scale with n, the reason for it is that it happens because of destructive interference. And so it happens because there are dark states, there are destructive interference processes that increase the variance. So the variance, you can make it large via 2 ways. You can either have some very high dominant channels, or you can have kind of radiative channels, but suppress many of all the others because of destructive interference. So this is what happens in 1D. And this critical distance is below 0.5. That is the distance that I told you, that is the maximum at which dark state exists. In 2D and 3D, the physics is completely different. So the critical distance in 2D scales sublogarithmically with atom number. And in 3D, it scales as a power law of atom number. So this means that the critical distance can be larger than a wavelength, and it can be larger than the maximum distance in the relative dimension below which there are dark states, which means that the origin of superradiance depends on dimension. So in 1D, superradiance happens because of subradiance, because of dark states, because of destructive interference. In 2D and 3D, superradiance happens because of constructive interference. So even though this is not a phase transition, because it's a purely transient phenomenon, so it's like the atoms are excited, boom, they go to ground state, that's the end. It's not in equilibrium, it's not a steady state. There are certain things that resemble phase transitions. So 2D is the critical lowest dimension. In 3D, there is superradiance basically for very large distances. And in 1D, the quantum fluctuations are not robust enough to hold the order. So in 2D and in 3D, this happens because you have enough atoms. In 1D, you don't have enough atoms, and there should not be Dicke superradiance. But it's a pathological case because of destructive interference. So if we would live in a world where there is no destructive interference, which is not possible, but if we would, there would not be Dicke superradiance in 1D. It would be forbidden, just like there is no phase transition of the IC model in 1D. It's not robust. Okay, so this is just an example of, well, I've been talking about two-level systems, but this physics can be observed in realistic atoms. So this is a collaboration with JQI at Urbana-Champaign, and he suggested the use of ytterbium. And ytterbium has this very interesting long wavelength transitions. So all these, even though the critical dimension, the critical distances can be quite large for 2D arrays, it's still, for realistic arrays that people can prepare in the lab, is still like 0.8 lambda. So that's a problem if you want to do optical tweezers, because it's hard to achieve small distances. So one way is to use these very long wavelength transitions. And so this is a plot, this is all preliminary, but it just shows that there are certain regions that are these green regions where one should observe superradiance in the system. And then I have an example of what happens in superconducting qubits, but perhaps for the sake of time, I can skip that. If you're interested in superconducting qubits, you can ask me. Yeah, so I will skip that. But superradiance also happens in waveguide QD, and there are very weird, even odd effects that we still don't understand. Okay, so with this, I've arrived to my outlook. I really think that this platform of atomic arrays are, kind of interesting merging of condensed matter physics and optics. And I just wanted to tell you some of the problems that I think are exciting. So one thing that we are starting to do is try to incoherently drive the system. So then you go to a steady state, and then you can make connections with actual phase transitions. And also perhaps something that is interesting is, well, in a cavity, we know that you can build a superradiant laser. Can you have such a thing without a cavity, just in free space? Once you realize that the dynamics is, at least for the early stages of superradiance, is mostly dissipative, one can come up with different ways of doing this numerical evolution. So we're trying to come up with new techniques for dissipative evolution. Even though I've been talking about superradiance all the time, one of the loves of my life is actually dark states, because this is how you can store excitations that live in a system forever. And so preparing dark states is extremely hard coherently, basically because they do not talk to light. So one option is to decay into them. So perhaps via feedback and measurement, one can tailor this very complicated stochastic evolution into a direction where you can deterministically prepare dark states, and hopefully those dark states have perhaps metrological or computational advantage. The idea that superradiance happens at distances that are comparable to the wavelength makes me think that perhaps this may be an issue in systems like arrays of Rydberg atoms for quantum computation. And so then following a question, I think one interesting thing is to revisit these experiments of superradiance in BC and in general in condensed phases, and try to understand the quantum optics there. And one thing that we are exploring now is many-body decay in waveguide QD, which I didn't have time to talk about, but I'm happy to discuss that if somebody is interested. And with this, I wanted to acknowledge my group and the people that are involved and leading this project, which is my postdoc Stuart Mason, my student Eric, and Sylvia has been doing the work on waveguide QD. And so if you're interested, you have these papers for references. I should mention that Francis Robichaud at Purdue has also published a paper where he takes our methods and extends them to directional superradiance. And also, I also wanted to mention this paper, a collaboration with Luis, which is what started our interest in many-body decay. And thank you so much. Happy to answer any questions. Yeah, so the question is the Hamiltonian doesn't make any difference. It does make little difference. Yes, at kind of up to the burst, it does not make much difference. I can tell you why, if that's the question. Yeah.
What is the interaction? Sorry, what is the dimensionality? Is it
The dimensionality is the dimensionality of the array. So whether it's 1D, 2D, 3D. Oh, the Lindblad is in this gamma ij's. This is the imaginary part of the Green's function. The Green's function is a two-body Green's function. So it's like it is the atom 1 interacts with atom 2. And so there, the dimensionality matters, right? So it will be very different if it's like a 1D array than if it's a 2D array. Also, the polarization is built in that. So it's the propagator of the field in between the different points where the atoms are located.
the dimensionality or the
It's both. Like you could increase the coordination number while keeping the dimensionality fixed, right? Like you could have like a cubic 2D, but you could have also a, I don't know, something with more neighbors that is still 2D, right? So your question is, if you start changing the geometry, if things change?
Yeah.
The geometry doesn't seem to be doing very much. I don't have plots here, but we have tried different lattices like honeycomb, a square, and so on. This doesn't seem to matter very much. It may matter, like there are some weird jumps that I can also talk about that for that the geometry matters, but for the global trends, it does not matter very much. Everything I said seems to happen in kind of any geometry, as long as the dimensionality, the dimensionality drives the origin of superradiance more than the geometry or coordination number.
So basically, it's that universal phenomenon.
Yes, that's why I titled Universality of Dicke superradiance.
But with higher level, like multiple level systems,
Multiple level systems. So we have looked at 2D. So the plot that I showed you with one excited state decaying to 3 intermediate states and then to a ground state. So this was a 2D array. And I don't know if you recall, but the superradiance could happen at distance around a wavelength. So this also seems to be the case for multi-level systems. But that part, while I think that my intuition still applies, I cannot promise you that it's true because we haven't checked higher dimensions with multiple level systems. Yeah, Christopher.
So I would figure it was really the density, not so much.
It's not the density.
Well, because, well, so you'll be able to tell me why I'm wrong. Because if I have more atoms that are within a fraction of a wavelength.
Yeah, but you cannot, right? Like if you are constricted to 1D, you cannot add more atoms. Like how can you add more atoms if you're in 1D? Like it has to be like in this side or in this side. Like you cannot put them anywhere else.
Sure. But if I have like a square lattice versus a diamond lattice versus something else.
That doesn't seem to be the case. Yeah. I think it's like higher dimension really enables for much more robustness. So there might be, I mean, there are differences with respect to the actual number of the critical distance, but there doesn't seem to be differences with respect to the scaling with n.
Oh, sure. Oh, yeah.
Yeah. So it's not that it's irrelevant. It's just not relevant for the scaling with atom number.
Hi, so this is Zachary Levine from NIST. Could it be my turn or?
I can't hear you.
Yeah, is that okay? Yeah. So my question is, there's some of these more traditional ways of looking at some of these systems, like a rate equation or a semi-classical field, and
yeah.
I was just wondering whether there was you could characterize the validity limit for some of these more traditional approximations and why you're out of it.
Sure. So I think in the 70s and 80s and so on, they were doing like semi-classical approaches where actually you integrate out the atoms and you keep like kind of nonlinear equations for the field. The issue there is that usually you lose the effect of graininess. And graininess in an ordered system matters a lot because it's what determines interference. So all these processes happen because of interference, either constructive or destructive. So if you now go to a region of like now a homogeneous kind of a polarization density, you may lose many of these effects. On the other hand, I have to say that when we started working on this and we looked at 1D arrays, and then I was like, oh my God, I have understood everything because decay superradiance happens because of subradiance, and all the papers that I read are wrong. In reality, that's not true, because there are papers that point to the fact that the direction of the emission of the light happens at the direction of maximum optical depth. So for instance, in 2D, it happens in the direction of the plane. This is true in 2D also with our methods, like the most radiative jump operator emits photons in the direction of the optical depth. In 1D, actually, is the opposite. So in 1D, because if you think of atoms directed along the chain, there is no far field emission. So actually, the emission goes out like that. And so actually, this is because the mechanism of decay superradiance is distinct. So it's I think it's hard to have most methods that you can do. The issue with them is that they are uncontrolled. So one thing that we're trying to do now is to do going beyond mean field. So basically, you have the equations of motion for the coherencies, and you do what is called the cumulant expansion. So you have like expectation values of many of these sigma spin operators, and you truncate them. And the issue is that this is uncontrolled. And even if you may be able, and I'm not sure you can, but you may be able to guess within 10% what is the height of the peak, which is something that we cannot do with our method. What you lose is the insight of like, why does this happen to begin with? And that's something that I think this idea characterizes it perhaps in a unique way. But I'm happy to talk more if you're interested.
Okay, yeah, no, great. Yeah, thank you. So, I mean, just as a corollary of what you've been saying, so if you had like a liquid, or, if the atoms were moving very quickly compared to the dissipative process, all of these effects would go away. Is that
Yeah,
true?
that's true. If there are decoherence mechanisms that are faster and that are not global but are local, it will disappear because there is no phase coherence anymore. Yes.
Right, which
So,
depends on the atom-to-atom spacing.
Yeah.
Right.
So for
specific
instance,
array.
in a disordered cloud, so people were looking at disordered clouds before. So in a disordered cloud, you have very high density of atoms, which might be good for emitting many photons. On the other hand, you have atoms that can be arbitrarily close. And so now the Hamiltonian that gives this 1/r³ term acts on these pairs of atoms and defaces them very fast. So superradiance is quenched. The good thing of the order arrays is that even though you have these 1/r³ terms, they are for all the atoms the same except at the edges. And the edges versus bulk goes as 1/n. So the effect of the Hamiltonian is very little because you have order in your system. So if you would have a cloud and you have disorder, then all these other processes will kick, and this will not be a good characterization of superradiance.
Okay, great. Thanks so much.
So I was wondering, so one thing we didn't talk about is the polarization of the light.
Yeah.
So I'm thinking in particular of if you have 1D chain of emitters, and this matter is X or Y.
Yeah. So initially all the atoms are inverted, so I'm not sending any light. And then what determines the polarization is the direction of the is the quantization axis of the atom, okay, which effectively is like the polarization of the dipole. And so that in 1D, I think I showed like in all plots I showed I think like different polarizations. So let me go back. So for instance, here is 2 polarizations, the only 2 relevant, and here as well. And so what matters is again like atoms, for instance, in this direction, they don't have far field dipoles in this direction don't have far field here. So for instance, if you have a 2D plane, if your atoms are perpendicular to the plane, the emission is going to be going in all directions in the plane. But if you have now atoms like that, it will be just in these 2 directions perpendicular to the dipole. So it does matter. And also the time matters. So in the beginning, the most superradiant jump operators will act, and then most of the direction will be like that. But then the remaining energy that remains after the burst will probably be in some dark state where also dark operators can act. So if you track the angular emission, it will be changing with the dynamics. It's not as trivial as it's always emitted in this direction, like it changes as a function of time. it changes as a function of time, interatomic distance, dimension, and dipole polarization.
Okay.
So I think we've peppered Anna with 1,000 questions, and so we should thank her again.
Thank you.